Hello there, welcome to another discussion of problems. This is episode number 13. Okay, so today we're going to talk about a very large class of problems that you encounter in introductory mechanics problems. They're called block and wedge problems. This is you can have a small block or a large block. The way we can distinguish a small block and large block is small block, you can just think of that as a point, and large block, its extent cannot be ignored. Okay, so in a small block, it's a can be on the wedge. There's a wedge, and there can be a whole bunch of different types of problems. We're going to just do a small block, but just for the large block, it's illustrated over here. You can have a phenomena called the block tipping over. The block kind of tips over. Okay, so that's really a new thing, and the question would be when the block will tip over. All right, so let's look at problems that you might encounter. Both the block, this block and the wedge can slide. So the block slides on this wedge, and this wedge itself can slide on a table. Let's call it table. This one I'm going to call it table. Table surface, and the table itself, it will be considered to be fixed. Okay, fixed to earth, and we're going to ignore the motion of the earth, ignore rotation of earth and translation of earth. So in all of these problems, those things are behind the scene, and you just ignore that. Okay, so if I were to take in any of these problems an axis like this fixed to the table, this will be an inertial frame. But if I had axis fixed to the wedge, this axis will be non-inertial, because the wedge itself will be sliding. So if the wedge is sliding, then it will be non-inertial if wedge sliding or accelerating somehow. Okay, so you can see there will be a problem type in which both wedge and the block slide. In another problem, which is the block slides, this is the most elementary one, but the wedge does not slide. This is like a often taught first. It's like what's the simplest situation I can imagine. Then you have a wedge sliding, but block doesn't slide. This is very weird. But there is a particular acceleration. If you the wedge has acceleration, the block actually doesn't slide, and then you have to figure out what are the conditions under which block does not slide. Okay, and then there is a angle theta. If you are allowed to vary this angle, then the question would be, when does the block slide? At what angle will block slide? So things that are given to you are kind of a static friction, kinetic friction coefficient for this surface here, surface of contact between the block and the wedge. Even though you can think of block as very tiny, it has a surface of contact. And if both wedge and block slides, you're also given these things. Okay, maybe if it's sliding, you only need this. If it's not sliding, then definitely static friction is responsible for it not sliding. Okay. There may be problems in which you might encounter that there is a force, maybe a force, additional force F on wedge. There may be maybe there's additional force on block. Okay, so there are these other things which can complicate it. So I'm going to come up with a problem that will just address. We'll just do this one and try to think of as complete as possible when that scenario happens. Then you're gonna be dealing with these kinetic frictional coefficients. Now, dealing with a static frictional coefficient is very tricky because a static frictional force magnitude can be less than or equal to a maximum value mu s, a normal force for that surface. So there will be over here static friction because less than that, unless the problem is describing to you that you should be using a maximum value for this, it becomes very tricky. So I'm going to just do a static frictional problem in a future video because this is a little tricky. So we're going to today just going to use this case and should be able to cover a lot of these other problems. Okay, maybe in the future I might do when I do the static, then I will be able to say, well, this thing will be like does not slide. And of course there may be a static frictional force that's involved in this. Okay, may or may not be, but we will do that. But today I'm going to do just a very general study of this case and including these additional forces on the wedge and on the block. And I'll set up a problem in which known will be listed and unknowns will be listed. Okay, you're gonna enjoy this. This is a very familiar problem to a lot of people. So let's think of the mother of all block wedge problems. All right, so both of these can slide. Both block and the wedge can slide, and we're given the mass of the blocks, the angle of the wedge is some angle which is fixed, and these we only need kinetic friction. So the friction force, kinetic friction force magnitude is equals to mu k, whatever the normal force is for that surface. So there will be a kinetic friction force for this surface, and there will be a kinetic friction force over here. So there are two different surfaces. They will have a different kinetic friction force. There's a normal force for this will be in that way. I'll call that N, and there will be normal force from the table on this block will be like that. So this will be on the block, and this will be on the wedge, and then there will be another one on the block. I will just write down this known forces just in a minute. Just so these are the additional forces on the block, additional force on the wedge, and acceleration of gravity. So these are all given. we're supposed to find the acceleration of this guy and acceleration of this wedge separately, okay, and the two normal magnitudes of two normal forces. And if you know the magnitude of two normal forces, you can figure out the corresponding kinetic friction. So this is the kinetic friction, and this is an equality. Unlike a static friction, this is equality. That's how you define what you mean by the coefficient, okay. And this is actually a good formula to remember. All right, so all of these problems, when you do a Newton's laws problem, you start with identifying the system and all the forces in that system. So here there are two moving bodies, so there will be forces on both of them. So you have to have like Newton's law for the block and Newton's law for the wedge. So you need all the forces on the block and you need all the forces in the wedge. You also need to, you learned from previous video that in order to use, say on block, so on block equals to mass A of block, you need to do this in inertial frame. And if you don't know what inertial frame is, go back to a couple of videos before and you will go over that, okay. So like a fixed frame, the frame that I have it over here fixed to something that's this table is supposed to be so-called fixed. You know, table is moving with the earth and you can say earth is rotating. We are going to ignore those effects, okay. In the last couple of videos I talked about how to take the effect of rotation of the earth into account, but for this particular set of problems we are not going to worry about the rotation of the earth. All right, rotation of the earth or revolution of the earth around the sun, we just say forget that part and they're not important for this problem, and we just do assume these are inertial frames. All right, having said that, right away you can say that if the wedge is sliding, a normal frame, normally people use this frame, so a frame that goes down the wedge. So this frame will be not inertial frame if wedge is sliding, so that it has non-zero acceleration with respect to the inertial frame, with respect to the inertial frame. So before you really do any problem, you got to figure out what inertial frame I'm going to use, and this is the step one, okay. Let me clean this up and we're gonna proceed. Okay, so let's find all the forces on the block first. So you know there's a gravity which is important to kind of realize there's a gravity, and all the other forces are kind of response to gravity, right? Of course this is also given somebody pushing on it or something like that, and the forces, we're going to assume all these forces are constant, so just everything is constant. So the forces are not function of time. That will complicate the problem, and we're not going to do that for these simple examples that you encounter in elementary physics problems. All right. So if you assume the block is moving downward and the velocity will be pointed downward on the wedge, then the kinetic friction will be opposing that. So that's one of the laws of the kinetic friction. Kinetic friction will oppose the direction of Fk. That's another thing you can remember. Direction of kinetic friction force is opposite to velocity, and that kind of makes a little bit difficult to write this analytically. So Fk direction is going to be like minus velocity over the magnitude of the velocity. So that's the direction times Fk. It will have a magnitude Fk, and the direction will be opposite direction of the velocity. We're not going to use this, but this is just one way to write analytically, and this turns out to be conceptually good, but not calculationally good. So we're not going to use this, although that is the law. All right. So we have assembled normal force. This is by wedge on block, and those are all the forces. So we have 1, 2, 3, 4 forces on the block. Now on the wedge, now these are pair forces. So if this is by the wedge on the blocks, when you write this on the wedge, there will be force opposite, same amount of force, but in opposite direction on the, like this is 90 degrees, this was 90 degrees, so it's going to be the same pointed downward. And I see this Fk is applied by the wedge, so this also by wedge on block. So there will be similarly, if that's the Fk that way, there will be Fk pointed down, which I kind of forgot to include that. There will be Fk pointed down. This will be the pair forces. This will be by block on wedge, and this is by block on wedge. When students study this subject first time, they kind of have a problem relating block and wedge, what's going between them. Not only their movements are coupled, which they tend to capture it, but their forces are also kind of internal forces between the block and the wedge, and they have to be paired up. There is an additional surface here. So there's a normal force here. I'm going to write down n prime for that, and that's from table on the wedge. And so this is from table on wedge, and the same thing is from table on edge for that n prime. So for acceleration of this guy, acceleration we're going to write with respect to the inertial frame is going to be x double dot I hat plus y double dot j hat, and the acceleration of this guy will simply be I will locate this wedge on the table just from its x coordinate of this point P. So we'll just capital X I hat, so double dot dot means ddt. Okay, so this is better way of writing than a sub x, a sub y, because you will see this x, this y, and this x, they're kind of related. All right, that's why it's best to use x double dot, y double dot, and things like that. And don't use a sub I hat plus a sub y j hat. Instead, use that way. Okay, you'll see in a minute why that is a more important way of writing it. Okay, so now we have forces, we have the acceleration. We just write F equals ma and just kind of grind through it, right? All right. I find it very helpful to redraw this picture like that. So all the forces are coming in this picture, in this redrawing. All forces coming out of a single point, regardless of where they were drawn earlier, while keeping the direction same. So, and this angle, you can see this angle, this is 90 degrees here, so this is 19, and this is 90 minus theta, and this is 90 degrees here. So this whole thing, this is the normal direction. Now, our axis is not along. Many times the axis, you have these axes you use many times, but in our case we are forced to use a different axis because of inertial frame. So we are using this axis, so that angle is very important to us. Okay, so this angle moves over there, and then you can see that this will make this as a theta, and so I can write all the forces in their vector notation. All right, so write down all the forces. You can start from anywhere. So this is weight. So like weight is opposite of y, j hat, so minus mg j hat. Let's write the normal. Normal is equal to it's at angle theta, which is y-axis. So this is going to be, this side will be sine theta, n sine theta I hat plus Sn cosine theta j hat. Okay, how about kinetic friction? This along that direction. So this is theta, this is 90 minus theta, so this is theta. So this is going to have a negative x minus fk cosine theta I hat, but positive y fk sine theta j hat. So fk is equal to mu k n. So this is already given, so this is not a new thing. So these are like if you find n, you find fk. So I can just leave fk as alone, or I can convert that into minus mu k n cosine theta I hat plus mu k n sine theta j hat. So we got this guy done, this guy done, this guy done. So only FB remaining. For FB, I'm just going to write down FB x I hat plus FB y j hat, and I don't need to convert to theta b, but we can always convert. Over here is going to be FBX and FBY, both will be negative. It will be minus FB cosine theta b, and FBY will be minus FB sine theta b. But in calculation, I just write it like that. Now we wrote all of this down. So all I have to do, and the acceleration for the block, the block is x double dot I hat plus y double dot j hat, and you can just write down. So mx double dot, just collect all of them starting from here, n sine theta minus mu k n cosine theta plus fbx. So that's one equation, and my double dot equals to, I just go to minus mg plus n cosine theta plus fk sine theta, which is I just violated my own rule of using symbols that are we know mu k n n sine theta plus fpy. So there you have it. These are the equations of motion for the block. Now we're going to do the same thing for the wedge. Okay. Okay. So now I took these forces and wrote it like I said earlier. For this wedge, we can do the same thing and wrote the axis appropriately and found all the angles that I needed to find. So we can just do W prime equals to minus capital mg j hat, and there's a lot more force here. N prime vector is n prime j hat, corresponding fk prime is on the x-axis, so this is fk prime I hat equals mu k prime n prime I hat. And continuing on, we have fw vector. We just again write over there just like this is our additional forces, if x I hat plus j hat. We could write that in terms of just like that from magnitude and direction. So we done this, we done this, we done this. We've not done fk. This fk vector is so if this is theta, this 90 minus theta, so this angle here is actually theta, parallel, these are parallel to the x-axis, so that's theta. So this makes angle theta. So this will be mu k n cosine theta I hat. This is going to be exactly opposite to that guy. So this is, we should say, write down star. So on wedge. So this is plus, and we could have just written down from there minus mu k. You can see that it will have a negative y component and the positive x component is fk. So mu k and sine theta j hat. So this, we could have just taken this, done this carefully, and put negatives everywhere. Okay, and then we have a, so we've done this, and then we do n. Let's call it n star. N star will be just the opposite of this guy, so I don't need to work it out. Minus n sine theta I hat minus n cosine theta j hat. And acceleration of the wedge is just x double dot I hat. Okay, so now we're going to write down its equation of motion. So I just go look for all the i's. So I get a mx double dot equal to mu k prime n prime, so this got done, plus fwx, that part, and plus mu k n cosine theta, that part, minus n sine theta. So this is equation number 3, and y component acceleration is 0, so 0 is equal to minus mg from here plus n prime from here, there's nothing from here, plus y from here minus mu k n sine theta from here minus n cosine theta from here, and that's it. So we have 4 equations. However, when you look at this, this x and x dot are not independent. They're related to each other. So one way to, there's a geometric constraint, and we are going to address that. So whenever you have two objects moving and they influence each other, their motion will be connected, and so you have to look for how they are connected. Are their variables connected? They are called constraints. And so if you look at it in this triangle, this theta will be same as that theta, and in here is x minus x, this side, and this side, let's call this height, it's arbitrary, but let's call it h, and so this h minus y. So basically y has to be less than h in this problem. You know, the domain of y is, it's like y has to be 0 and make it all the way down here and all the way up here, h. It has to be between these two, and x has to be, you know, x can be anywhere on this, but y has to be between that. So ratio of this is same as, if you take a ratio of that, it will be same as ratio of these guys, or tangent theta has to be equal to that. Theta is fixed, so you can say tangent theta equals to h minus y over x minus x, or you can just say x minus x tangent theta equals h minus y. So if so this is not very simple actually, not just x to x relationship between not just between this and this, but all three are connected. So if I take a time derivative, this arbitrariness goes away, and so we have a constraint equation. It says that x double dot minus x double dot tangent theta equals to minus y double dot. So this is equation number 5. So we have 5 equations, and they're sufficient to actually solve for all the things we wanted to solve for. Okay, so let's look at a symbol we wanted to solve for, and I'm going to just mark it. So things which are not known, this is not known, this is not known, this is not known, those are knowns. This n is not known, and everything else is known here. F's are given, n prime is not known. So you can see that you have 5 equations and 5 unknowns, and I can just bulldoze through this thing, right? Just eliminate till I find the answer. I'm not going to do that algebra, but you can just carry out the algebra. You can solve for these 5 things by plugging in, and be careful meticulously. Take a page of calculation, just pure algebra. But conceptually, this is how you set up the problem. Things which are kind of, you might not see right away, but if you have some experience, you can see that in these couple problems, so a constraint is was important, because if I didn't have constraint, I won't have 5 equations. I'll have 5 unknowns, but I'll have only 4 equations. That's a dead giveaway. That my Newton's laws of motion generated 4 equations which had 5 unknowns, and so I couldn't really find them unless I have the 5th one, and the 5th one comes from the constraint, the geometric constraint in the problem, and so you have to go look for it. Sometimes it's not very obvious. It's very obvious here, but if you look for it, that maybe the motion of one is related to the motion in the other. You might see you may have a conservation of momentum, angular momentum you apply, and from there you can find this kind of constraint. This one is a simple problem. I think I'm going to stop here. This should give an idea of the procedure that it takes to actually set up a problem like block on wedge, even a more difficult problem like this. You just have to have patience and algebraically go over this. I find just writing these vectors, like writing as vectors, is very important. And also another important is using x double dot, y double dot, especially when you got two objects or three objects which are kind of interacting with each other. Because if you don't like this, then discovering and making use of constraint becomes nearly impossible. Okay, so with that advice, I'll stop. If appreciate if you hit the like button. You can check out my website here. So just a reminder, helps the like button helps distribute this content a little bit more. I'll see you in another video. Bye.